In this investigation, we will be identifying an unknown dye using the relationships between absorbance and fluorescence. This report was conducted and recorded by Ali Cadu, Dawson Sloan, and John Robertson. The main problem in this experiment is that a cuvette contains an unknown dye in water solution at an unknown concentration, and what physical experiments can we conduct to identify these unknowns? In addition, how can these experiments tell us more about fluorescence? Our goal in this experiment was to use a flashlight and spectrophotometer to acquire absorbance and fluorescence spectrums. In addition, identifying key wavelength ranges with regard to fluorescence. We hypothesized that creating absorbance and fluorescence spectrums would allow us to identify our sample compared to known values. We also hypothesized that the excitation and emission wavelengths will be different of our fluorescence dye. Our results showed that our dye was indeed sawtelle dye, and that our fluorescein dye was excited at different wavelength ranges than what was emitted.
Our experimental design involved measuring absorbance using a mag light, stained with a ruler, fiber optic spectrometer, and ocean optics software. We collected data by focusing the mag light at the cuvette 40 centimeters away and holding the spectrometer on the opposite side from the light source. This was done for both our dye and water. Fluorescence was collected by shining a mag light directly into a fluorescein-containing cuvette. However, this time the fiber optic cable was held 90 degrees from the source direction. Measurements were recorded the same way using the ocean optics software.
This is the setup we used to measure the absorbance of our unknown dye and of our fluorescein. Each trial, we had focused light shining 40 centimeters away through the cuvette and to the sensor that is held next to the cuvette to not allow in any ambient lighting.
This diagram resembles our fluorescence model of our experiment. There were two critical steps when gathering fluorescence data. The first one was a dark environment to make sure that the only light coming in was from our flashlight and not from ambient light around the classroom. In addition, a 90-degree measurement angle was a critical step. This was to avoid measuring the excitation wavelengths of light coming in from the flashlight, and at 90 degrees we are only measuring light emitted from the sample.
Absorbance can be calculated using Beer's law. This involves dividing the intensity values of the light transmitted through the dye and water and taking the log of that quotient. This absorbance was then plotted against the wavelength of light to create an absorption spectrum, which was compared to known spectrums to determine the extinction coefficient. The maximum absorbance value was then divided by the extinction coefficient and path length through the cuvette to determine the concentration. The fluorescein absorption was calculated the same way as the unknown dye. The intensity values collected through the emission were scaled down and plotted with the absorption against the wavelength to analyze the trend.
Absorbance is the measure of how much light is trapped by a solution, and fluorescence is the measure of how much light energy a substance emits after the absorption of a particular wavelength. Also important to note is that the wavelength emitted is usually larger and thus has less energy. This loss of energy is due to the transfer of kinetic energy through neighboring molecules.
The absorption and fluorescence of the fluorescein at each wavelength is shown in the graph to the left. We see that the wavelength of light absorbed is smaller and thus higher energy than the light emitted by the fluorescein in the presence of the mag light. The absorbance spectrum of our unknown dye was compared to a known spectrum, both of which are shown on the right, allowing us to determine its identity and thus the extinction coefficient required to calculate concentration. At the maximum wavelength of our absorbance, 495 nanometers, the concentration was calculated as previously mentioned and was determined to be 2.7 times 10 to the negative fifth molar.
Multiple factors had the potential to provide experimental error in our experiment. First, ambient light around the classroom from other groups shining their flashlights or lights from the windows could have provided different levels of ambient light at different times throughout our trials. Also, the cuvette had different surfaces on each side, and it was difficult to put the sensor at the exact same spot on the cuvette for each trial. Finally, the mag light had trouble staying on, and this could be inconsistent I/O across our trials.
We determined our dye to be sawtelle dye based off known absorbance spectrum. Comparing the spectrum also let us find the extinction coefficient to calculate our concentration. For our fluorescein, looking at the absorption and emission graphs, the magnitude of the wavelength emitted is less than the magnitude of the wavelength absorbed. This difference is known as Stokes shift. Since the dye has to move up to an excited energy state, it will require more energy. The excess energy dispersed is due to vibrational energy relaxation.